Hello friends. Have you ever wondered what actually happens inside your computer when you open 10 apps at once and somehow they all keep running, even when your RAM is much smaller than what those apps want? The answer is a clever trick called paging. In this video, we'll look at what paging is, why operating systems use it, and how it quietly powers almost every device you use, from your laptop to your phone. Let's break it down. Alright, before we get into paging, let's understand the problem it solves. Every program you run, your browser, your code editor, a game, wants memory to do its job. And often, the total memory all your programs want is way more than the RAM your computer actually has. So the operating system has a real challenge here. How do you run big programs, and many of them at once, when there simply isn't enough physical RAM to hold everything? That's exactly the puzzle paging was designed to solve. Let me show you the core idea. Here's the core idea behind paging. Instead of treating a program as one giant block of memory that needs to fit somewhere, the operating system chops it up into small, equal-sized pieces. Each piece is called a page. A typical page is around 4 kilobytes, but the exact size depends on the system. Now, why equal sizes? Because equal pieces are easy to manage. Think of it like cutting a long document into uniform A4 pages. Once everything is the same size, you can shuffle them, store them, and find them without any awkward gaps. That's the trick. The program no longer needs one big continuous space in RAM. It just needs room for its individual pages, scattered wherever there's free space. Now here's the other half of the trick. The operating system also splits your physical RAM into equal-sized slots, and each slot is exactly the size of one page. These slots are called frames. So you have pages on the program side and frames on the RAM side, and they're the same size by design. That means any page can go into any frame. It's a bit like a parking lot where every spot is the same size as every car. You don't care which spot a car parks in, as long as there's an empty one. This simple decision is what makes the whole system flexible. The operating system doesn't have to hunt for a big continuous space anymore. It just drops pages into whichever frames happen to be free. And this is where paging really starts to shine. Look at what's happening here. The program thinks of its pages in a neat order. Page 1, page 2, page 3, and so on. But in actual RAM, those pages can be sitting anywhere. Page 3 might be at the top, page 1 somewhere in the middle, page 5 down at the bottom. They don't have to be next to each other, and they don't have to be in order. This is a huge deal. It means the operating system can use every little gap of free RAM instead of needing one big empty stretch. It's a lot like how files get scattered across your hard drive over time. The file still opens correctly because the system keeps track of where every piece lives. But that raises an obvious question. If the pages are scattered all over RAM, how does the program ever find them? That's where the next piece comes in. Meet the page table. This is the secret sauce of paging. For every program running on your computer, the operating system keeps a little lookup table that maps each page to the frame it actually lives in. So when the program asks for page 1, the OS checks the table and says, page 1 is in frame 6. Page 3? That's in frame 1. It's basically a contact list. The program knows the name, and the page table knows the address. Every program gets its own page table, because every program has its own pages scattered across RAM in a different pattern. This one small table is what lets pages live anywhere in memory, and still be found instantly. It's the bridge between what the program thinks its memory looks like and what RAM actually looks like. So now you can see something really elegant. There are basically two views of memory. The program sees a clean, ordered, continuous stretch of memory. Page 1, page 2, page 3, all lined up neatly. This is called virtual memory. It's the illusion the operating system gives every program, so the programmer doesn't have to worry about what's really going on underneath. But the actual RAM, the physical memory, looks completely different. The pages are scattered, mixed in with pages from other programs, sitting wherever there was free space. The page table is the translator between these two worlds. Every time the program touches memory, the OS quickly converts the virtual address into the real physical address. The program never knows the difference. This is exactly the kind of trick Chrome uses too. Every tab thinks it has its own clean memory space, but in reality, they're all sharing your RAM, and the OS is juggling it behind the scenes. Now here's where paging gets really powerful. What happens when RAM fills up completely, and a program still wants more memory? The operating system has a clever move for this too. It picks a page in RAM that hasn't been used in a while, copies it out to your disk, usually into a special area called a swap file or page file, and frees up that frame. The new page that was needed gets loaded into the empty frame. This back and forth is called swapping, and this is the real reason your computer can run programs that are bigger than your physical RAM. Only the pages you're actively using need to be in RAM at any moment. The rest can sit quietly on disk until they're needed again. It's the same idea as keeping only the books you're reading on your desk and leaving the rest on the shelf. Of course, disk is much slower than RAM, so when too much swapping happens, your computer starts to feel sluggish. That's the famous "my laptop is thrashing" feeling. So let's pull this all together. Why does paging matter? 4 big wins. First, no wasted RAM. Because pages are small and equal-sized, the OS can slot them into any free gap, instead of leaving awkward empty stretches. Second, program isolation. Each program gets its own page table, so one program can't accidentally read or mess with another program's memory. That's a huge deal for security and stability. Third, you can run bigger programs. Thanks to swapping, the program isn't limited by how much RAM you have, it's limited by your disk space, which is usually much larger. And fourth, smooth multitasking. The OS can juggle 10 or 20 programs at once, because it only needs to keep the active pages in RAM. Every modern operating system you use, Windows, macOS, Linux, Android, iOS, relies on paging to do all of this quietly in the background. Alright, quick recap. Programs get split into equal pieces called pages. RAM gets split into matching slots called frames. The page table keeps a map of which page lives in which frame, so the program always finds what it needs. And when RAM gets full, pages quietly swap out to disk and come back when needed. That's paging, a small, elegant idea that makes modern computing actually work. If this helped you finally understand what's going on inside your computer's memory, hit that like button and subscribe to Webronaq so you don't miss the next one. We'll keep breaking down these core computer science ideas in plain English. See you in the next video.